Recall that the conjugate of the complex number w equals a plus bi, where a and b are real numbers and I is equal to the square root of -1, is the complex number. Conjugate of w is equal to a minus bi. For any complex number z, let f of z equal 4i times the conjugate of z. The polynomial p of z is equal to z to the fourth plus 4 times z cubed plus 3z squared plus 2z plus 1 has 4 complex roots, z sub 1, z sub 2, z sub 3, and z sub 4. Let q of z equals z to the fourth plus az cubed plus bz squared cz plus z. Be the polynomial whose roots are f of z sub 1, f of z sub 2, f of z sub 3, and f of z sub 4, where the coefficients a, b, c, and d are complex numbers. What is b plus d? So first off, let's do some backtracking. We want to find b plus d. We know that by Vieta's formula, b is equal to the pairwise sum of these roots. So b equals f of z sub 1, f of z sub 2, plus f of z sub 1, f of z sub 3, plus etc. D is going to equal the product of all these roots. So f of z sub 1 times f of z sub 2 times f of z sub 3 times f of z sub 4. So how do we find these? Well, first off, we know that f of z is defined to be 4i times the conjugate of z. What is one property we know about the product or sum of conjugates? So if we have two complex numbers, x and y, the conjugate of x times the conjugate of y is equal to the conjugate of x times y. And the conjugate of x plus the conjugate of y is equal to the conjugate of x plus y. So we're going to use these two properties. First off, let's take a look at b. b is equal to, right, f of z sub 1 times f of z sub 2. That is the same thing as 4i times the conjugate of z sub 1 times 4i times the conjugate of z sub 2. So simplifying this, we get 4i squared times the conjugate of z sub 1 times z sub 2. So then we can apply this to every single other pair. That gives us plus 4i squared times z sub 1, z sub 3, plus 4i squared times z sub 1, z sub 4, plus 4i squared times z sub 2, z sub 3, plus 4i squared plus z sub times z sub 2, z sub 4, plus 4i squared times z sub 3, z sub 4. So this is just all the pairs expanded out. And then let's look at what d is. So d is going to be the product of all of these. So similar to b, we have 4i multiplied 4 times. So 4i to the fourth. And then we have a product of z sub 1, z sub 2, z sub 3, z sub 4's conjugates. But that is just equivalent to z sub 1, z sub 2, z sub 3, z sub 4 all multiplied together, taken the conjugate of. So that is our value of d. Now let's look at what these are, respectively. This and each of these. Well, we can see from over here that we can first rewrite our b as 4i squared times the sum of all these pairs. So the sum of all these pairs is the same thing as the sum of all these pairs and then taking the conjugate of it. And if we think about it like that, we have the sum of z sub 1 plus z sub 2 times z sub 2 plus z sub 1 times z sub 3 plus blah, 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 all the way, all the pairs. And then we take the conjugate. Well, that seems to just be the conjugate of the pairwise sums of the polynomial p sub z. So we can just use this value 3. We get this is equal to 4i squared times the conjugate of 3. And then let's look at this product. Well, we have our 4i to the fourth still, and we're taking the conjugate of this product here. What is this product here? Well, the product of all the roots z sub 1 through z sub 4 is just going to equal 1. So this will just be the conjugate of 1. Now for b, we have the conjugate of 3 is just 3. So 3 times 4i squared is 16 times -1 gives us -16. So b has the value of 48. And then we look at d. So conjugate of 1 is just 1 times 4i to the fourth is just negative 16 squared, which is 256. So now we're asked to find what b plus d is. That is just going to equal negative 48 plus 256, which is equal to 208, which is answer choice D.